So we're going to take a short break from talking about probability distributions, and we're going to talk about this sampling part of our diagram that we've been talking about all semester. Then we're going to start talking about probability distributions again, but now with respect to a statistic that comes about through that sample. So how do we actually take a sample? I've mentioned before there are a wide number, or there's a wide variety of different ways to take a sample. And in fact, there are whole courses on sampling, typically in a department of statistics. We're just going to focus on, in this particular class, one way to take a sample. It's the easiest. It's called a random sample. So a random sample is a sample from the population where every item that's in the population has an equal probability to be included in the sample. So how do we do it? Well, here's the easiest way. Suppose you could number all the items in your sample from 1 to capital N. We can then just simply use the sample function R with, let's say, a vector of these 1 through N to take a random, and then use the sample function to take a random sample of size little n. So for example, let's take a look at this very simple example. Let's say that we have a very small population. Let's say it's only a size of 20, and we want to take a random sample of size 10 from that. We number all items from 1 to 20, and then we use the sample function to sample from 1 to 20, and we're going to sample 10 of them. And so the very first item in our sample is 17, the second item is 14, the next item is 19, and so on. Notice how I set a seed here. We've talked about seed numbers before, and the reason why I do that is so that I can reproduce my results at another time. Of course, if I use a different seed number, then what will most likely happen is I'll get a different sample. Let's say instead our population has a size of 25,000. Maybe that represents 25,000 students at a particular university. In case I didn't say this properly, this is actually the population size of 25,000. And what we'd like to be able to do is take a sample size 100 from that population. And so again, what we can do is use that sample function where we sample items from a vector of 1 to n, and we're sampling little n of those items. So the very first item in our sample is number 19,628. The next one's 13,653, and so on. To put it in the context of sampling students, perhaps instead of having 1 to n here, you could instead have student ID numbers as a vector. Put that in a sample, and then you get your sample out. So here's an important question then. Should you use the same seed number every time that you take a sample? So maybe you want to take a sample from one university, and the next time you want to take a sample from another university. Maybe the next time you want to take a sample from another university after that. Should you use the same seed number? Well, no, because now you have a way of kind of interconnecting the different universities, and essentially it's no longer a random sample from each separate university. Now there are other ways to take a random sample as well. Here's an older way that's often still discussed in some textbooks. If you're interested in learning about it, I have it here in my notes, but I will not ask you a question about it on a test. Okay, now let's talk about things called sampling distributions. All that a sampling distribution is a probability distribution for a statistic that comes about through a sampling process. That's all it is. So to help explain it, let's suppose we have random variables y1, y2, yn that represent items that we would get in our sample from a particular population. Now this population, though, we don't know a whole lot about it in terms of the actual probability distribution. We don't know. But let's say that each random variable has the same population mean and the same population variance as well. So some questions then. Is y bar then a random variable itself? Well, obviously, it's a function of random variables, and so those random variables can vary from one sample to the next. And so, yes, indeed, y bar can vary from one sample to the next. So, yes, it is a random variable. Is a lowercase y bar a random variable? And the answer to that is no, because remember, these are observed values, or a way to symbolically represent the actual observed values that you get from a sample, and that's just essentially from one particular sample. Now, what we would like to be able to do is have some general idea of our random variable y bar. What would it be on average from this sampling process? Let's say if I were to repeat the sampling process many times, take one sample of 100 maybe, take another sample of 100, take another sample of 100, and calculate y bar every single time. What on average would all those sample means be? And that's essentially what the expected value of y bar actually represents. And one could actually mathematically prove that it happens to be mu, where mu is then this population mean of y1, it's the population mean of y2, and so on. So y bar itself, its purpose is to actually estimate mu. And look what happens. On average, we would expect y bar to get it right, essentially. A really cool result. In a similar manner, you could also talk about the variance of y bar. So maybe you can think of, let's say, taking a sample, thinking of the variance of that sample, taking another, let me restate this. Take a sample, calculate a y bar. Take another sample, calculate a y bar. Take another sample, calculate a y bar. Keep on doing this over and over again, and calculate a variance of all those y bars. That's essentially what var of y bar is representing. Of course, that also then would mean this is the expected value of y bar minus mu squared. Remember before how we've had the variance of y is equal to the expected value of y minus mu, that quantity, squared, where mu, again, is the expected value of y. The same concept applies here when we're finding the variance of y bar. And again, one could show mathematically that this is actually equal to sigma squared divided by n. And let me just emphasize, well, where does one actually prove this mathematically? That will be the purpose of a mathematical statistics course. So look at the result though. So let's say if I take a sample size of 10, maybe instead a sample size of 100, maybe instead a sample size of 1,000, what is happening to that variance? Well, since that n is in the denominator, as that sample size grows, that variance is going to go down. Let's think of an intuitive reason why that should happen though. Well, as we get more and more information from about our population, in other words, my sample size goes up, one would expect then y bar to essentially become a better and better estimator of what mu is. And so thus there's going to be less variability of y bar with respect to where mu is, or mu's value. So there's going to be less variability then. You're going to get a better result, and that's represented by having a smaller variance, just because you have more information as that sample size goes up. Again, a very good result, or interesting result. And on a test, I could ask you to explain to me basically what I just discussed here. So if it's not clear, you do need to ask about it. One could also think of the standard deviation of the y bars itself. That would, of course, just be the square root of the variance. So, why are these items important then? Well, what this does, it helps us determine the characteristics about the sample mean even before we actually take the sample. This is going to be very, very useful to us as we do stuff like, for example, to do inferences. And we can even go further. So you can see how I'm getting excited about this, because this is a really cool section. One can actually show that the probability distribution of y bar itself, in other words, the sampling distribution of y bar, is approximately a normal distribution with a mean of mu and a variance of sigma squared divided by n when the sample size is large. This result is known as the central limit theorem. This is probably the most important result in all of statistics. At least it's up there. So again, we don't know anything about the probability distribution of y1, y2 down to yn. But that doesn't matter. Y bar itself, as long as we take a large enough sample, so we have a good enough information about the population, let's say, this probability distribution of y bar itself is approximately normal, has an approximate normal distribution. Okay, so some notes. So the distribution of statistic y bar here is often referred to as a sampling distribution. Again, multiple terminology to mean the same thing. We can talk about the sampling distribution of y bar, or we can talk about the probability distribution of y bar. They are exactly the same thing. The reason why we call it also a sampling distribution is that y bar results from a sample. Well, what though is a large sample though? Well, it depends. Generally speaking, if your sample size is greater than or equal to 30 for a situation like this when we're dealing with y bar, you're probably going to be okay. That normal distribution is going to do a decent job. However, it can do a very good job even if you have a lower sample size than 30. It just depends upon if you somehow knew what the underlying probability distribution is for the population, meaning the y's, y1, y2, yn. It just depends upon that. And in fact, then that essentially gets into what some people do for statistical research, is they look into those kinds of things, like how good is this normal distribution approximation if, let's say, y1 through yn has some really weird, funky distribution, a probability distribution to it. Okay, and then I guess also on this note, I just emphasize why this is important. Now, I would say probably most books will represent the central limit theorem with this expression here. Let's talk about this. So remember, we've had if y has a normal distribution, where it has a mean of mu, variance of sigma squared, we can also look at, or we can also use a standard normal distribution with a transformation of y minus mu divided by sigma. So in that same, or using that same idea, then, since y bar has an approximate standard normal distribution, if we subtract off mu, if we subtract off the standard deviation of y bar itself, then we get a quantity, we can call it z, that has an approximate standard normal distribution to it. Again, most books will actually represent a central limit theorem, the corresponding result this way. I don't think it's really necessary, but I bring this up because you may see it like this. Now, there is a problem, though, with the central limit theorem, and that is we need to know mu, we need to know sigma squared. How do we get around that problem? We'll talk about that later in our course. Okay, so let's take a look at an example. The purpose here is to do basically a little bit of a what's called a Monte Carlo simulation to show you that indeed the central limit theorem does work. So let's say I sample 20 students, and I repeat the sampling process 1,000 times. This is with respect to the GPA example. So I go out and take a sample of 20. Then I go out and take another sample of 20. I do that 1,000 times. Also, let's say that the probability distribution in the population representing these GPAs is what we've seen before, where we have this, what would be a left-skewed distribution. Remember, in this particular case, the mean GPA was 2.86 about, and the variance was about 0.41. So in my program itself, I'm not going to go there. You can look at it on your own. I actually go through the sampling process of taking 1,000 samples. How I went about doing it for this particular problem, you're not responsible for. Instead, what you're responsible for is understand the results from the sampling process being repeated 1,000 times. So here is the first 14 observations from the first sample. So the very first person had a GPA of 3.41, the next person 2.79, and so on. Here are the last 6 observations as well from that first sample. Here's the second sample, the first 14, the last 6 from the second sample, and so on. So I have this all arranged into rows and columns. So with that then, what I like to do is take the mean of the first row, take the mean of the second row, and so on. A quick way to do that in R is to use a function called row means. So if I say row means and then set 1, that's where I have all this information stored. What I have here now in Y bar are 1,000 different sample means. And so if I look at the first 6 of them using the head function, we see the first sample mean is 2.96, the next one's 3.11, the next one's 3.21, and so on. Here's a histogram of all the sample means. I've rescaled the y-axis here so that I can also plot a probability distribution on top of it. In my program, I show how to do that. Please take a look at it. And what we can see from this histogram is it's roughly symmetric, mound shape, like a normal distribution. And this particular normal distribution that I've plotted on there it's a normal distribution that has that same mean that we had before, which was 2.86, I believe. Let me just double check. Yes. And also has then a corresponding variance of sigma squared divided by n. So n would be 20, and sigma squared was 0.4082. And so we can see that indeed this central limit theorem does hold for this particular example. Even though the underlying probability distribution that we had for the population of all GPAs was left skewed, when I look at the sample mean, I still get an approximate normal distribution. A really cool result. Well, what would be the mean of all those y bars? This is like actually computing the expected value of y bar. And I get 2.85. Remember, again, mu was 2.86 essentially. So we can see how close we are. The standard deviation was 0.1337. Again, that should be sigma divided by square root of n. It should be really close. And I think actually on the next page, I actually show what that is, 0.143. Again, very close. Well, what about probabilities now associated with this, this approximate normal distribution? Or, well, yeah, I guess we can phrase it that way. Let's first take a look at this probability of having that the sample mean GPA is between 3 and 4 by thinking in terms of these 1,000 simulation values. So we've seen some of these ideas before. So y bar itself has 1,000 y bars in it. And if I do y bar less than 4, what this is going to give me is a bunch of trues and falses. So in other words, I'm going to have 1,000 trues or falses throughout. Actually run this on your own to see that that happens. And then if I do some kind of math with all those trues and falses, such as sum them up, R is going to convert the trues to 1s and the falses to 0s. And what this is going to give me is the number of y bars that are actually less than 4. Then I divide by 1,000. Now note, of course, college GPA cannot be greater than 4. So in fact, this sum should be 1,000. But if I come over here and look at y bar less or equal to 3, well, now what's going, and I guess I should have just had less than there, excuse me. No, I guess that's right. Because of that. Now you might be thinking, wait a second, Chris, you just told me it doesn't, or you told me not too long ago that it doesn't matter if you have the equal sign in there or not. And in a practical sense, that doesn't matter here. But in this particular case, we're actually dealing with actual observed values for the sample mean. So I suppose we could have a case where it is actually equal to 3. Try it with the equal sign without, I bet you'll get exactly the same answer. So y bar less or equal to 3. So get some trues and falses. Those trues and falses becomes 1s and 0s when you sum them up. Divide by 1,000, so you get the percentage of times that you do have y bars less than 3. And overall, you get 0.138. Now, if we would do the corresponding calculation with an actual normal distribution itself, we will find probabilities with the normal distribution. The quantile that we're at is 4. Here's our mean. Here's what that standard deviation would be, corresponding to what the essentially what the central limit theorem says. And then we also do the same thing with 3 as well. And look what we get, 0.16, very close there. Why is it so close? Well, again, take a look at the shape of the histogram. Take a look at the shape of the probability distribution plotted on it. They are very similar. That's why those probabilities are close. Now, the purpose of this was just to kind of give you a proof by example. It's not a formal proof. A proof by example that indeed the central limit theorem does hold. In an actual situation, you're not going to take 1,000 samples of size 20 to do something like this. You know, in terms of like the GPAs, take 1,000 samples of size 20 GPAs from a university. But rather, because this worked out, we can simply rely on the central limit theorem alone and calculate probabilities. Okay, so let's take a look at another example. We've done a lot of examples already with the normal distribution as well, so at least finding probabilities associated with the normal distribution here should be quite simple. But I still want to go through one example like this. And this deals with what I call cereal boxes, or the example is called cereal boxes. Suppose a cereal manufacturer claims that it fills boxes on average with 24 ounces of cereal. Also, suppose an FDA official wants to determine if the cereal boxes truly, have the advertised weight of 24 ounces. What the FDA official does, it randomly samples 36 boxes of cereal and checks that how much they are filled with. Now, this is kind of a quality control example here, you could say. The central limit theorem can be used to help out. So suppose the cereal boxes are actually truly being filled correctly with a mean of 24 ounces, standard deviation of 2 ounces. Perhaps it's a little bit too much, but that's okay. What is the approximate probability the sample mean weight is actually greater than 23 ounces? Notice I'm not saying anything about the actual probability, that, like giving a name for a probability distribution here. Now, let's actually look at a plot of what that probability distribution, this probability distribution now of the sample mean would look like. So here's just our regular old normal distribution. I use a curve function to actually draw it. And we want to know what's the probability that y bar is greater than 23. So let's plot 23 here, and it's like, whoa, look at that. That probability should be huge, or at least close to 1. Now, to find this particular probability, remember, if we are going to use the p-norm function R, we have to essentially look at a complement instead. So we find 1 minus the probability of y bar less than 23. So we put 23 in there for the quantile. We put what that mu should be. And also we put in what the standard deviation should be. Note that a big mistake that students often make is that they forget that square root of n right there when we're dealing with the central limit theorem. Our probability is indeed very, very close to 1. Well, what is the approximate probability that the sample mean weight of the boxes is between, let's say, 23 and 25 ounces? Remember what the FDA official wants. He or she wants it to be within 1 ounce. And so to find this particular probability, we again break things up into 2 parts, like what we've done before. Then we use the the p-norm function, and we get a very high probability. So on a test, then, I will often ask you a question like this. Well, do you think that the FDA official is going to find something wrong with how they're filling the boxes? Well, given this result here, the answer would be no. It would be very unlikely. Here's the actual probability of finding it. Okay, so that is the end of this particular set of notes.